Hello everyone, this is Srilika K. I am pursuing Sri Venkateshwara College of Engineering, Bengaluru, Department of Electronics and Communication Engineering. Today I am here to present technical seminar on LEO small satellite constellations for 5G and behind 5G communications under the guidance of Meghavarshini SK, Assistant Professor of ECE Department. These are the contents which I am going to explain. Introduction, literature review, objectives, methodology, results, and conclusions and references. Coming to the introduction, the constellations of small satellites are operated in LEO. These small satellite constellations are working together as a communication network, completing 5G new radio and behind 5G communications. LEO has low manufacturing cost, less size and less weight, under 500 kg when it is compared with medium Earth orbit and GEO known as traditional big satellites. These qualities of LEO reduce the launching costs. LEO constellations have become an attractive option for delivering high bandwidth, low latency communication services to users around the globe. LEO is relatively closer to Earth and is commonly used for satellite imaging as they capture high resolution images. The satellite based communication system is called Land Mobile Satellite System. It provides efficient benefits to remote lands, aerial services, sea, and global communications. The application of low Earth orbit or machine to machine, mobile broadband communication, device to device, broadcasting, and more. The satellites in LEO do not always follow a particular path around the Earth. Their planes can be titled. The LEO provides faster communication and has a high bandwidth. For global coverage, many satellites will be needed in the mega LEO constellation. Individual LEO satellites are not so useful to serve the purpose because the satellites move speedily over the sky and this requires a lot of work to track such satellites from the ground station. The LEO satellites assist areas with terrestrial wireline and wireless networks. The satellites in LEO act together as the communication network that presents the output to support the fifth generation 5G of wireless technology and a faster network. These constellations deploy at the altitude in the range of 500 and 2000 km and their combination with 5G new radio provides near global coverage and support. First one is it enhances mobile broadband services to increase user data transmission rates, and second one is huge machine type communication allows a range of Internet of Things to work over large geographic areas. And last one is ultra reliable communications gives one-way latency guarantees in 30 meters second with a 2 meters second propagation delay between the ground and LEO. These are the diagrams. These diagrams overview of the unique characteristics of LEO small satellite constellations with respect to traditional GEO satellites. LEO small satellite constellations are also generally lower in cost than traditional GEO satellites, both in terms of individual satellites, cost, and the total number of satellites needed to achieve global coverage. This makes them an attractive option for a range of applications, particularly those that require frequent revisit times and low latency. In particular, the ground coverage of a LEO satellite deployed at 600 km above the Earth's surface and with a typical elevation angle of 30 degrees is around 0.45% of Earth's surface. Moreover, due to the low altitude of deployment, LEO satellites can communicate with diverse types of ground terminals such as dedicated ground stations, 5G ships, and other vehicles or Internet of Things devices. Finally, LEO satellites move rapidly with respect to the ground at up to 7.6 km second for an altitude of 500 km. but also with respect to each other in different orbital planes. This leads to two main challenges. First, the constellations are dynamic, usually entailing slight asymmetries that are aimed at minimizing the use of propellant when avoiding physical collisions between satellites at crossing points. Therefore, dynamic rather than fixed mechanism must be put in place to create and maintain in the links. Second, these links experience a much larger drop shifts than those found in terrestrial system. Then coming to the diagram of a Walker star Leo constellation with established intra and interplane ISLs. The Walker star Leo constellation with the established intra and interplane ISLs enables global communication and internet services, providing high-speed connectivity to people and business around the world. The physical links are the broadly classified in GSL and ISL. A GSL between a dedicated GS and a satellite illustrated is also called as feeder link. The availability of a GSL, the satellite path is determined by the ground coverage and the orbital velocity. Due to the high orbital velocities of LEO satellites, these passes are short and frequent handovers between satellites are necessary to maintain connection between the ground terminals. The optimal path corresponds to that in which at some point in time the satellite crosses over the observer's zenith point. ISL can be further divided into intra and interplane ISL, where intra for satellites in the same orbital plane and interplane is for satellite in different orbital planes. Furthermore, the ISL between satellites in orbital planes moving in nearly opposite direction that are one ascending and one descending are known as crossings. Coming to the literature survey, these papers which I referred. First paper is LEO satellites in 5G and behind networks. A review from a standardization perspective. These authors are Tasnim Darwish, Michael Belmare, Kara Bullet Kurt, which is published in the year 2021. And these bronze are to provide an overview of the current status and potential of low Earth orbit, which can be informative for researchers, engineers, and policymakers interested. And coming to the cons, it is based on the current state of research and standardization activities and may not reflect the future developments and market trends, which can unpredictable. Coming to the second paper, here satellite constellation for 5G and behind, how will it reshape vertical domains? These authors are Shikong Liu, Zhen Gao, and Katkit Wong. This published in the year 2021, and the pros are this can provide high-speed internet connectivity to areas that are currently underserved, which can help to reduce the digital divide. And the cons, they may raise privacy concerns as they can potentially collect and transmit large amount of data about users. And the coming to the third paper, battery-aware contact plan design for LEO satellite constellations. Authors are Karsten Gerstacker, Holger Hermans, Christian Bay. These published in the year 2020. And coming to the pros, it can enable more efficient use of the limited bandwidth available to LEO satellites. And the cons, it may require new standards and protocols to ensure the interoperability and reliability with existing satellite or ground-based system. And the last paper, large-scale constellation design for the Internet of Space, Things or CubeSats. Authors are Han Kak, Ian F. Achildes. This was published in the year 2019. Pros are analysis of the technical requirements and design considerations for a large-scale CubeSat constellation, which can be useful for researchers and engineers working in this area. And coming to the cons, design is based on the certain assumptions and simplifications such as a uniform distribution of IoT devices and a fixed orbit altitude which may not hold in reality. Objectives of this paper are to understand the differences between polar and geostationary orbits, to provide reliable communication, and to analyzing the feasibility and performance. And last one is to provide in-depth understanding of modern modulation, coding, and multiple access schemes. Next is advantages. Advantages are flexibility, easy inputting in new circuits, distances are effortlessly taken care of, and expense doesn't make a difference. Broadcasting conceivable outcomes. Each and every side of the earth is secured. Users can control the system. And last one is energy is conserved since satellites are use solar power. And the disadvantages are costs are prohibitive. Satellites are expensive. Signal reception can be spotty. Problem with satellites is they somewhat unreliable signal. Propagation delay is problem. And the last one is there are no repair shops in space. And next is application. These are the applications. First is weather forecasting. Without the help of satellites, we cannot predict weather. Military satellites, satellites for navigation, global telephone backbones, connections for remote or developing areas, global mobile communication. Coming to the methodology, the GSL and ISL in terms of propagation delay, Doppler shift and achievable data rates, unless otherwise stated, the results presented were obtained by simulation with parameters for the satellite transmitters, whereas a fixed transmission power is defined for the ground terminals. This is the 95th percentile of the propagation delay and Doppler shift at the physical links. The, the effective isotropic radiated power density is the designed parameter for the satellite transmitters, whereas a fixed transmission power is defined for the ground terminals. The constellation is a Walker star, which I explained before in introduction. The Walker star as illustrated with P polar orbital planes deployed at a minimum altitude of 600 km. The orbital separation, that is altitude increments of 10 km. Each of these orbital planes can consist of n satellite. The 95th percentile of propagation delay and the Doppler shift for each physical links in the constellations. The latter is calculated as the Ft equals Vfc by c, where V is the relative speed between the transmitter and the receiver, Fc is the carrier frequency, and c is the speed of light. The propagation delays of less than 4 meters second are typically in the GSL. Besides, similar propagation delays were achieved at both the intra and interplane ISL with a total of 480 satellites. Such short delays are physically unattainable in GEO system and enable multi-hop transmission that comply with the requirements established by the 3GPP for the user and control plane latency of 50 meters second round trip time. That a Doppler shift of nearly 600 kilohertz is typical in the GSL, which is comparable and even greater than that in the interplane ISL. This is because cross-seam ISL were not implemented. This is a common practice, for example, followed in the upcoming Kepler constellations because of the huge Doppler shift when the satellites move in nearly opposite direction. For instance, if the cross-seam ISL are implemented with p equals 7 and n equals 20, the 95th percentile of the Doppler shift width is 1.46 megahertz. As a reference, the system bandwidth for NB-IoT is only 180 kilohertz. In contrast, the intraplane ISL are not affected by Doppler shift because the intraplane distance are rather stable. Coming to the median and 95th percentile of the data rates at the physical links in an interference-free environment. This median and 95th percentile of the achievable instantaneous data rates at the physical links in an interference-free environment. That is, the rates are chosen from an infinite set of possible values to be equal to the capacity of an additive wide Gaussian noise channel at specific time instance. Naturally, the distance in the GSL and in the intraplane ISL are less variable than in the interplane ISL. Because of this, the 95th percentile of rates is similar to the median in the GSL and intraplane ISL, but much greater for the interplane ISL. And next is the logical link. A logical link is a path from the source transmitter to the end receiver. Hence, data travels over many different physical links which may not be known by the two endpoints. In this case, there are two different kinds of endpoints, a satellite and ground terminal, which enables the definition of four logical which may utilize one or several of the physical links GSL and ISL. These are four logical are illustrated: ground, ground to satellite, satellite to ground, satellite to satellite. First is ground to ground. Classical use of the network where information is relayed between two distant points on the ground is also used for handover, routing and coordination of relays. And ground to satellites is mainly used for maintenance and control operations initiated by the ground station, for example, to distribute instructions for ISL establishment and routing, but also for caching and telecontrol. Satellite to ground is relevant when the satellites collect and transmit application data, such as in Earth observation, but also needed for handover and link establishment with GS, radio resource management, fault detection, and telemetry. And last is satellite to satellite. This satellite to satellite mainly relevant for satellite related control applications such as distributed processing, sensing, and routing, possibly exploiting distributed intelligence. Also used for topology management, including neighbor discovery, link establishment, and other autonomous operations in the space segment. The use of the different physical and logical links is tightly related to the final application. In Leo constellations, we identify not only applications that are inherited from terrestrial network, but also those that are native to space communications. The IoT devices wake up periodically to send status updates. These updates are forwarded within the constellation until reaching the nearest satellite to the destination with an established link to a ground terminal. This end-to-end application relies on ground-to-ground logical link. Naturally, the satellite to ground is needed to retrieve The information in ground beside the satellite to satellite link can be exploited for cooperation among satellites, for example, to point the cameras to a particular position when a first spacecraft detects an unusual event. Next is the results. This is the result. As a result, 95th percentile of the propagation delay and Doppler shift at the physical links in a Leo constellation indicates that 95% of the links experience propagation delays and Doppler shifts are lower than the reported values, while 5% of the links have higher values. This indicates that the majority of links in the constellation experience relatively low delays and Doppler shifts, which is generally desirable for reliable communication. The median and 95th percentile of the data rates are the physical links in an interference-free environment. These metrics indicate the typical and highest achievable data rates in the absence of any interfering signals. The median data rate represents the middle value of the data rates. This indicates that 95% of the link can achieve data rates lower than the reported value, while only 5% of the links can achieve higher rates. The performance of the physical and logical links in a Leo constellation, lower propagation delays and Doppler shifts, and higher data rates are generally desirable for efficient and reliable communications. Coming to the conclusion of this paper, in this paper describe the main opportunities and connectivity challenges in LEO small satellite constellations. Besides, they characterized the physical links in LEO constellations in terms of propagation delay, Doppler shift, and achievable data rates. This result showcase that LEO constellations have the potential to fulfill the 5G promise of true ubiquity and to support the generic use cases of enhanced mobile broadband and huge machine type communication characteristics, and hence must be with latency requirements of a few tens of milliseconds. Nevertheless, these physical links present different characteristics and hence must be properly designed to unleash the full potential of the constellation. Furthermore, they provided an overview and taxonomy for the logical links in connection with the used physical links and relevant use cases. Results illustrate the potential benefits of adaptive coding and modulation schemes in the GSL and of proper resource allocation for multiple access in the ISL. And the last is references. Thank you.